Okay, this is our last lesson on collision theory and transition state theory that deals with something called reaction mechanisms. Now, in the last lesson, we learned that as a reaction goes from reactants to products, it transitions through something that we call the activated complex. And in doing so, it breaks bonds and makes bonds such that we result in the products that the reaction results in. But it turns out that for many chemical reactions, there actually isn't one reaction, but there's actually a series of smaller reactions that takes place very quickly that results in what we see as the overall reaction. So what we want to look at today are these series of smaller reactions that results in what we perceive as the reaction we want to study, and that's called a reaction mechanism. So let's get some definitions here. So a reaction mechanism is a series of steps that makes up an overall chemical reaction. So it turns out that most chemical reactions don't just take place in one shot, that there are subsequent smaller steps that then overall result in what we perceive as the overall chemical reaction. So now that we know that there are these little steps, we need a name for them, and each step is called an elementary step, right? Elementary means simple, right? So it's an elementary step involving single molecular events, very simple collisions involving one or two reacting particles. Now, this the order of the reaction in the rate law with respect to each reaction in an elementary step is the same as the coefficients in the balanced chemical equation. All right, now this is where we have a big change. And it involves a rate law. So now we're going back, way back to that lesson where we learned how to write out the rate law. And that rate law had a particular form. It looked like this. The rate is equal to some constant k times a to the exponent x times b to the exponent y, etc., etc. Now, when we taught you about the rate law, we said that x and y could only be determined experimentally. All right, and that was the experimental side. Remember, I talked about there being an experimental side and a theoretical side. Well, a reaction mechanism is a theoretical idea. And when it comes to elementary steps, we can get the x and the y directly from the coefficients. Now, this is different. I told you you could not use the coefficients to determine the rate law experimentally, and that is still true. But when it comes to an elementary step, a simple step, the rate law is the same. All right? It is the same as the coefficients in the balanced chemical equation for that elementary step. And this is because this is coming from theory. And I'll explain a little more of that in a moment. So that's a little change about an elementary step. So let's take a look at this particular reaction. Here we've got two NO molecules reacting with an oxygen to produce two NO2s. Now this reaction, you might think, again, just happens in one shot. But in actual fact, this is unlikely. And that's because we have three reacting molecules. And as soon as you have more than three reacting molecules, that means that these three objects, right, NO, NO, O2, that means they have to all collide at the same spot at the exact same point in time. And that's highly unlikely, right? Collisions of two objects take place all the time. Think about a car collision. Two cars collide at an intersection, and that's a common occurrence. Very rarely do you have three vehicles colliding at the same point at the same time. You might say, yeah, Mr. Sanders, but what about a car pileup where there's lots of crashes? Well, even if you were to look at that, you would notice that there are usually only two particles colliding at the same time. Car A may hit car B, and that collision may cause a subsequent collision with car C, etc., etc. So whenever you have three particles colliding, this is a very unlikely situation. All right? Very unlikely. Okay? And so we need to now think of a mechanism. What's actually happening in this particular reaction? So here's a proposed mechanism. Again, this is theory. All right? Chemists sit down, they start thinking, what do we think is happening here? What kind of reaction is happening? So here somebody's proposed a particular mechanism. Here we've got one of the NOs reacting with an O2 to produce something called an NO3. And this NO3 then exists for a brief moment in time, and it subsequently runs into the second NO, thus transferring an O over to the other NO. That then results in our NO2. And here we've got the overall reaction. And that overall reaction can be obtained by adding the reactions together, much like we added reactions together with Hess's law. You can see here we've got an NO3 as a product in step 1 and an NO3 as a reactant in step 2. And when we're finished, we can add them all together and we can get the overall reaction. So here we've got a reaction mechanism. Now notice in the side here we've indicated that one reaction might be slow and one might be fast. It's hard to determine exactly how or why that is. It can be done theoretically by looking at the bonds of the reactants. But for now, let's not worry about where that comes from. Let's just imagine that we know that one of them is slow and one of them is fast. Now, a couple of terms that we need to deal with. One, reaction intermediate. The NO3 in the last reaction, I'll back up there, the NO3 in our last reaction is a reaction intermediate. And that's because it is produced in one step and then consumed in a subsequent step. All right, you can see that. The rate determining step is another very important statement. In all multi-step processes, whether it is a chemical reaction or whether it's the manufacture of a bicycle, there will always be a slowest step. And the overall process of making, whether it be molecules or bicycles, can never be faster than the slowest step. And so there's always a slowest step that controls how quick the reaction can be. And we call that the rate determining step. It is the slowest step. And notice, we'll link this to our knowledge on transition state theory. That slowest step is the one with the highest activation energy. Each step in a reaction mechanism has its own potential energy diagram with its own delta H and its own activation energy. And the step that has that highest peak, that greatest activation energy, will be the slowest. And that's going to determine the rate of the overall reaction. Now, this is a very important statement here. The rate law of the equation for the overall reaction will be the same as the rate law for the rate determining step, all right, for that slowest step, all right? So if we go back and take a look at what the slowest step was, let's go back a couple here. The slowest step in this case is NO plus O2 to get NO3. And if I go back one more slide, sorry, 2 slides, it says the order of the rate in a rate law with respect to each reactant in the elementary step is the same as the coefficients. So here's where we have that thing that's the same as the coefficients. So if I go ahead here, and you'll notice I've got NO, O2, slowest step. Both of these have a coefficient of 1 and 1. That means if I go to the rate law right here, that I will have a rate law of NO with an exponent 1 and O2 with an exponent 1. And these ones came from these ones right here. So I'm going to stress that one more time. Because this is the slowest step, if I go back and I see that the coefficients are 1 for each of these things, and I now go ahead, then my coefficients for the overall rate law will be 1 and 1. All right, and that's because the slowest step determines it, and the rate law will be that. So this is how our theory can hopefully connect with our experimental determination. So that's very important. So what we've been talking about here is the rate determining step, the slowest one. It's got the highest activation energy. And if we want to determine the rate law, we can get it right from those particular things. And I'm going to erase away that marking so that we can take a look at that. Let's take a look at those ones. All right, I want to make sure we can see the ones. So a little important summary here. A reaction mechanism is a best guess. It's a theory as to how might the reaction occur. What makes up a good reaction mechanism, a reasonable one? Containing elementary steps with no more than 3 reacting particles each, because 3 things colliding are very rare. It'll always have a slowest step, which is consistent with the rate law of the equation. So therefore, we want our theoretical slowest step to have the same rate law as our experimental one determined in the lesson where we were calculating rate laws. And it has an elementary steps that add up to give the overall equation. If they don't add up to give the overall equation, well, then it just doesn't make any sense. All right, let's look at some examples here. Oh, no, another definition. Catalysts. A catalyst is present at the beginning of one step and produced in a subsequent step. It is generally not included as part of the overall reaction. Let's take a look. So, in this particular reaction, we have A plus B to get C. Then we have C plus D to get E and B. And if you take a look, if we were to add these up, you'll notice I can cancel C, just like we did before. But I can also cancel B. Now take a look. Notice the C was produced. It was a product. And then it was used. It was a reactant. Okay? We already have a word for that. That's called a reaction intermediate. We saw that on the last couple of slides. But notice, B is a reactant first. And then in the end, it's produced. Which means in the end, it will come back out of the equation unaltered. That is a catalyst. Is that right? So a reaction intermediate is a product first, then a reactant, and a catalyst is a reactant first, and then a product. And now we've got some information on that. So let's take a look at an example on a type of question that we could have here. I'm going to bring the whole thing up here for the questions, kind of a silly order. Whoops, too far. Let's back it up. So let's take a look. We're given some information here. You can see here I'm given step 1, and we're telling you it's slow. We could have given you an EA value, and this EA value would have been the biggest number out of all of the EA values. But instead of giving you the EA value, we're telling you that this is slow. And we're telling you that the delta H is greater than 0. In other words, it's endothermic. And here we've got step 2, and it is fast and exothermic. Fast and exothermic. Fast and exothermic. And in the end, the overall reaction is exothermic. So let's go through and answer these. What is the overall reaction? What are the reaction intermediates? What's the rate determining step? And what is then the rate law that we get from the rate determining step? And putting all 4 steps together, can we do a potential energy diagram? Okay, well, let's take a look. Let's cancel away things that we find on both sides. If we look at step 1 and step 2, you'll notice we've got HO2Br, HO2Br. You'll notice it starts as a product and then a reactant. That makes it a reaction intermediate, HO2Br. Continuing on, you'll notice we've got an HOBr, two of them on the right, and you'll notice two of them get used up subsequently there in steps 3 and 4. And therefore, that also started as a product, ended as reactants, therefore it is also a reaction intermediate, HOBr. And if I look around, I don't believe there's anything else I can cancel away. So let's write the overall reaction down. By the looks of it, I've got 4HBr plus O2. Yeah, and that reaction will not happen in one shot. You've got 5 particles that need to collide with each other. That just isn't going to happen. And on the product side, you'll notice I've got 2H2O and I've got 2Br2. All right, so we've determined the overall reaction. We've determined the reaction intermediates. Now let's take a look for the rate determining step. Recall that the rate determining step is always the slowest. That means the rate determining step is the first step of this particular reaction, HBr plus O2 to produce HO2Br. Excellent. So now we're ready for the rate law, and this is the important one. The rate law, remember, comes from the rate determining step. It comes from that slowest step. It comes from the coefficients of the elements, the molecules in the rate determining step. Which means then our rate law is R equals K times the concentration of HBr to the exponent 1 times the concentration of O2 to the exponent 1. Again, those ones end up in our rate law from the mechanism. All right. So now finally, the potential energy diagram. Well, this particular diagram is kind of a neat thing to see, and is really a mixture of a bunch of potential energy diagrams put together for each step. So let's move on to the next slide and set it up. In this case, I'm going to make a nice big set of axes here. Could have been a little straighter, but that's okay. Again, we've got our reaction progress, and we've got our potential energy. And the first overall thing that I'm going to look at is the fact that the delta H for the entire reaction is negative. So I'm going to go from top to bottom so that we can see that. Now the first step is slow, and it is positive. So if we take a look back at the first step, and I'm going to see if my writing sticks, hopefully it does. It is slow, and it is a positive delta H. That means it's going to have a big bump, and it's going to be endothermic. All right, excellent. This part says slow because it's big, and right here we've got endo. Now you don't need to write that in, I'm just stressing it. So now if we go back to the others, let's look at the rest of the steps. You can see here that it's fast and exo, fast and exo, fast and exo. So I need 3 more steps that have small bumps and exothermic reactions getting me to the bottom. So we'll have a small bump exothermic, small bump exothermic, and the last one a small bump exothermic. All right? So you can see there that in the end, my overall reaction from there down to the bottom, way down to there, delta H is negative. All right? And so you can see here again with our analogy from the last lesson about a ball. If you imagine we have a ball here, we try to push it up that hill. It's going to need a lot of energy to get over that first hill because it's big. But once it gets over the first hill, it's going to have enough energy to roll its way down to the bottom to the products energetically. So we need a lot of energy to break those first bonds. And once those first bonds are broke, the energy we get out of it will allow all of the energy, all of the particles to come together and make the products. So a couple of little things to note here. This guy right here, this EA is small, all right, and that results in it being fast. I wrote it backwards compared to the last one, all right? And then in this case, you'll notice this reaction here is exo, right? So that's delta H positive, right? Delta H negative. Again, here we've got delta H negative, and again, delta H negative. All right? Okay. So again, it's kind of just a sketch. Let's take a look at another one here. If this reaction took place in one step, you don't know if it doesn't. The question is asked, what if it did? What would be the rate law? Well, if it did happen in one step, again, I'm looking at the coefficient. Rate, K, concentration of N2O5, 2, right? That 2 comes from there. The actual rate law for this reaction mechanism was, and you can see here that the exponent is 1. There it is. What might be the rate determining step? All right. Well, if it's got a number 1 in it, then we have to have a step that only contains 1 N2O5. And this is where you can be a little creative. There is no officially right answer to this. It just simply means that I have to have the number 1 in the coefficient for the start of my reaction. So why don't we then just have this particular thing spontaneously break down into something like, well, we're trying to get to N2O4, so maybe we have N2O3 and an O2 falls off. That makes good sense. And so somehow then maybe another O2 bumps into that and turns it into N2O4. But that's not what the question asks. The question asks what might be the rate determining step. And because this has a number 1 in the first position, right there, number 1, and this is plausible, it makes good sense, then you have succeeded in predicting maybe a rate determining step. So here we've got another one here. So here we've got another reaction. NO2, 2NO plus 2H2. Not likely happening in one step. 4 particles, that's not going to happen. Here we've got N to produce N2 and 2H2O. And we're told the rate law. We're looking at the number 2 right there, and we're looking at the number 1 right there. Is the following mechanism a reasonable one? Well, let's take a look. First thing I see here is that the first step is slow. That makes it the rate determining step. The next thing I do is I go straight to those coefficients, right there and right there. We know that those coefficients have to be in the rate law, and are they? 2 and 1? You bet. That looks good. That is reasonable. I would say yes. All right? The coefficients of the rate determining step are the same as the exponents in the rate law. It does make sense. It is reasonable. Okay, so there you go. The question sheet will either be handed to you or you can track it down online. There are some questions also out of the textbook concerning reaction mechanisms. And there are some chapter review questions out of the textbook in preparation for the test. And there are some answers to the question sheets. Again, you can get that on the note on the PowerPoint online. You can go back and see that. And those are some textbook answers. Those are old, but you can also get them online. Okay. That means we are done the portion on rates, which means we are now preparing for a test. Or, sorry, you are preparing for a test. Have a nice day.